one or two questions that I was asked at the break convinced me that I had been less than crystal clear in describing this experiment. So just let me go through some aspects of it again. So this is a pulsed laser, and the pulse lasts about 10 nanoseconds. And we use that to dissociate the hydrogen peroxide that's in this cell here and generate OH. This is another laser. So this is a solid-state laser that pumps a dye laser, and that dye laser is tuned to a specific frequency at which the hydroxyl radical will absorb. This again is pulsed, and it lasts again about 10, 15 nanoseconds. That pulse goes into the cell and excites the OH, which fluoresces, and we measure the fluorescence on a photomultiplier. And the intensity of that pulse of light coming out of this reaction cell gives us a measure of the hydroxyl radical concentration present at that time when this probe laser fired. And what we do is we change the time delay between these two lasers and build up a decay. Now, you may not be able to see this, but that time there is a millisecond. So we're looking on timescales of maybe 10 microseconds to a millisecond. And so these are quite long times compared with the 10 nanosecond laser pulses. So the width of those pulses are unimportant. They're essentially instantaneous compared with the timescale of the reaction. And so we build up this decay, and from that we can analyze and get the experimental data. Why are we doing it? We're doing it, and much of this lecture course is going to be about this. We're doing it to generate rate constants for reactions which are of relevance in combustion. And OH plus SO2 is significant in combustion because of the presence of sulfur impurities. So I hope that all of the reactions that I show you are of relevance. And there are many, many, many of them. And so you have to do lots and lots and lots of experiments in order to cover them. And we'll discuss that later on. OK, now this is a new slide. What I thought I hadn't really explained was what I meant by secondary reactions. So what we want to be able to do is to use this simple pseudo first-order approach for a single reaction, just one reaction that's dominating our system. And to do that, we've got to make sure that secondary reactions play an absolutely negligible role. Now, what do we mean by secondary reactions? This involves keeping the initial radical concentration as low as we can possibly make it. And there's a beautiful paper by Vagjani and Ravishankara from 1991 that looks at this reaction, OH plus methane, going to CH3 plus water, important combustion reaction, important in the atmosphere. And they demonstrated that many of the studies that had gone before gave poor rate constants because the radical concentrations were too high. And it's a paper that's well worth looking at if you're interested in this sort of thing. As I said, typical radical decay time scales in pulse photolysis reactions are of the order of 0.1 to 1 millisecond. We produce OH, and the OH generates methyl radicals. And methyl radicals can react with OH. And if that reaction is too fast, then it's going to play a role in the decay of the hydroxyl radical. Now, the rate constant for OH reacting with CH3 is very fast. It's of the order of 10 to the minus 10 centimeters cubed per molecule per second. What it means is that pretty well every collision between CH3 and OH leads to reaction. The time scale for removal of OH by this reaction is 0.1 seconds for CH3 equal to 10 to the 11 centimeters per centimeter cubed. Just let's show what I mean by that. What we're doing is we're looking at that rate constant, which is 10 to the minus 10, I won't put the units down, multiplied by CH3. And then we're looking at 1 over that. And that's going to tell us about the time scale of this secondary reaction. Okay? So if CH3 is equal to 10 to the 11 per centimeter cubed, CH3 has got a concentration of 10 to the 11 per centimeter cubed, then that time scale is 0.1 seconds. And if it's 10 to the 13, then it's a millisecond. It's comparable with the timescale of the reactions we're looking at. So we can't afford to have methyl radicals present in concentrations of the order of 10 to the 13 per cc. And those CH3s are generated from this reaction. And so if we have OHs of the order of 10 to the 13 per cc, then we're screwed. We're going to get secondary reactions occurring. So you've got to keep the concentration of OH down as much as you possibly can to of the order of 10 to the 11 per centimeter cubed. If you think of that at atmospheric pressure, that's 10 to the 11, 10 to the 19. That's 1 part in 10 to the 8. So it's really quite a low concentration. And so to do that, you need to have a very, very sensitive technique. And that's what laser-induced fluorescence is. So you need a sensitive detection technique, and LIF is ideal. And when we come to talk about shock tubes later on, then this is a very important consideration there, just how sensitive the detection technique is. Okay, so that slide will be in the final set of slides that you get, that goes on the web. Okay, let's have a look at one or two other techniques, detection techniques. Whoops. So this is using time of flight mass spectrometry. And so what we've got here is a flow tube, and the precursor and the reactants are flowing down this flow tube. And then you have a laser pulse, an excimer laser pulse that goes through it and generates OH, which reacts away with whatever it is you're wanting to look at. Or you could have some other species that reacts away. And then what you do is you have a pinhole here, and the material comes, and the skimmer, the material comes out of this pinhole, and you hit it with a vacuum ultraviolet laser pulse that ionizes the species you're looking at. So you might, for example, be looking at the methyl radical in that reaction we've just looked at. You might look at the methyl radical, and so you would photoionize the methyl radical and any other radicals that are around. And then you use time of flight mass spectrometry to detect the methyl, to identify the methyl, and determine its concentration. The great thing about this technique is that it's universal. Laser-induced fluorescence has the problem of only being able to look at certain species. Hydroxyl radical, it's very, very good with, but other species, it's not so good. For example, methyl. So this is time of flight mass spectrometry using vacuum ultraviolet photoionization. Now, this is taken to extremes at the advanced light source in Berkeley. The advanced light source uses radiation from a synchrotron, so vacuum ultraviolet radiation from a synchrotron. And the great thing about the synchrotron is that you can tune the wavelength that you're putting into your reactor or your reaction cell. And so we can change the photon energy of the light that's doing the photoionization. And this was an experiment, a classic experiment published in Science, which looked at different flames and looked at the concentrations of acetaldehyde and ethanol. And it doesn't take you very long to notice that those have got exactly the same the same overall formula, the same mass. They both have a mass of 44. And if you used ordinary mass spectrometry, ordinary ionization techniques, electrons or non-tunable radiation, then you wouldn't be able to distinguish between them. But with the advanced light source, what you can do is you can change the photon energy, and ethanol has a lower ionization energy than does acetaldehyde. And so you can see here that as you change the photon energy, you get a mass 44 peak coming in here, well below the photoionization energy for acetaldehyde. And this is ethanol. And then the acetaldehyde kicks in up here. And these are different flames, propanol, cyclohexane, propyne, benzene, all showing the presence of ethanol as well as acetaldehyde. And so this hadn't been demonstrated at all in flames previously, but this is the great advantage of the advanced light source. And there is a similar system in China at the National Synchrotron Radiation Laboratory. And this is a similar set of experiments there using butanol flames, and again, looking at ethanol and looking at acetaldehyde. And so this is different ratios of ethanol and acetaldehyde, 20% ethanol, 80% acetaldehyde, 40% ethanol, 60% acetaldehyde from different flames. So getting different ratios of products in these different flames. As far as pulse photolysis is concerned, then you can also use this advanced light source technique. So this is rather like the method I showed you before. Here's a reactor. An excimer laser pulse produces radicals. The radicals come out of a pinhole, go through a skimmer, and then into this, you hit them with the tunable synchrotron radiation, and then they go into a mass spectrometer here. And this is a sector mass spectrometer. And these experiments were done looking at this species, which is called a Kriege intermediate, CH2OO. And it's very important in the atmosphere, but it had never, ever been observed. Its presence was presumed, but it had never been observed. And so what they did was to take CH2I2, photolyze it, and produce CH2I, and then react that with O2. And the reaction of that with O2 generated CH2OO. So you can see from here that this is the mass 46, which corresponds to CH2OO. And the ionization energy is about 10 electron volts. It could be other things of the same mass. This ring species here, which is called dioxirane, or it could be formic acid. But these are the photoionization efficiency curves for dioxirane and formic acid, and we're getting this Kriege radical being formed at much lower ionization energies than is the case for these, showing very clearly the presence of that species, CH2OO. And this is the CH2OO reacting with SO2 and decaying away different concentrations of SO2. And again, a pretty classic paper published in Science using this technique using this technique at the advanced light source. Okay, let's go and have a look at a slightly different sort of problem. So this is looking at a reaction between allyl radicals. So we've got C3H5 reacting with C3H5. And allyl is a key intermediate in many flame systems, many combustion systems. Now, there is a complication here, because if we look at this, dC3H5 by dt is going to be minus 2, as we said yesterday, times K times C3H5 squared. And if we look at the solution of that differential equation, it looks like this. 1 over C3H5 is equal to 1 over C3H5 0 plus 2 times K times T. It's a second order reaction, second order in radical, and we need the concentration of C3H5. We said with first order reactions it doesn't matter, we don't need the absolute concentration, but in this case we do need that absolute concentration. And so this technique is designed to allow you to determine that concentration absolutely. And so what it uses is, it's 1982, so it's quite an old experiment, but it uses, again, a laser to produce allyl radicals in this reaction cell here, and then uses white light going through the cell and then into a monochromator. And what you're doing is you're measuring at a specific wavelength the absorption within the cell by that C3H5 radical. And you're using something called Beer's law. So this is Beer's law, which says the amount of light coming out of the cell divided by the light going into it depends exponentially on the concentration of C3H5. This is the absorption cross-section, and that's the path length. So basically what you're doing, here's your cell. The light is coming through, and you're looking at a particular wavelength, but you've got an intensity going in, an intensity coming out, and you measure these two quantities, the light before and the light afterwards. Okay, so we need the absolute concentration, so that means we need this cross-section here, which has got to be measured separately. And that's the decay curve for C3H5. Those of you with an eye for such things will immediately see that that's not an exponential decay. It's a second order decay. It slows down. As the reaction proceeds, the concentration of C3H5 is decreasing, and so the reaction is getting slower and slower and slower as you go on. Okay, here's another even more complicated reaction to try and determine the reaction between CH3 and H. So again, a radical-radical reaction, but we've got two different radicals now. So what you do is you use, again, laser flash photolysis to produce the radicals, but you produce much less H than CH3 by adjusting the conditions. So CH3 is there in much larger concentrations than H. You detect H by resonance fluorescence, which is somewhat similar to laser-induced fluorescence, and CH3 by absorption. And you need the absolute concentration of CH3 because that's what's determining the rate of removal of H. We only need a relative measure of the hydrogen atom concentration, but we need to know absolutely the concentration of CH3. So you use absorption then to determine what the CH3 concentration is. And there's the decay of the hydrogen atom, and there's the decay of CH3. And these are the experimental results. The CH3 absorption is analyzed according to this expression here. which comes from 1 over CH3 is equal to 1 over CH3 naught plus 2K2T, where K2 is the rate constant for CH3 plus CH3. And dt is, delta I is the difference between, delta I is I naught minus I. So it's the amount of light that's been absorbed in the cell. And delta naught is the peak optical density. So that's the definition of delta naught. And I won't go through the derivation of this, but from here, using the definitions of d of t and delta naught, you can easily derive this expression. The hydrogen atom concentration is determined by, sorry, these are also new, so these weren't on the original slide, I'm afraid. dH by dt is determined by K1, the rate constant for reaction between hydrogen that's varying with time, CH3 that's varying with time, minus some loss process. The hydrogen atoms, for example, diffuse out of the region which you're observing. But they could also react with other species. So from this equation, integrating this equation, and using the time dependence of CH3, you can get an expression for H, which depends analytically on the amount of CH3 that's there, determined by this quantity delta naught, defined up there. And so it's a fairly difficult experiment to do, but you can get there in the end. This was done by a PhD student of mine, and basically this was what he did during his PhD. He built this apparatus and he measured these rate constants. And this was some time ago, and in those days you used to do something called plotting on a piece of graph paper. You didn't do it all on a computer, you actually did it by hand. And I remember very well the piece of graph paper which eventually became this plot here as he measured these various rate constants, which each of them took a very long time. And this piece of graph paper got grottier and grottier and grottier as the years went by. And it was covered with blood and vacuum grease and tears. It was, it really was a labor of love. But he's now a very, very, this guy, Mark Bruard, who is now a professor at Oxford, so he did okay in the end. Okay, so those are the rate constants as a function of temperature and pressure, because it's an association reaction. And here, because it's a pressure-dependent reaction, we can define high pressure limiting rate constant, low pressure limiting rate constant, using the techniques that we talked about before, and these are those high pressure and low pressure rate constants. There is a mistake here, because that should be centimeters to the 6, molecules to the -2, seconds to the -1. Interesting, because this is actually taken from the paper. So the error is there in the paper. I've just noticed it. Now, just let's talk a little bit about this analysis to get these high and low pressure limits. You recall an earlier slide we had where A plus B reacts to form AB star, which then goes on to be stabilized to form AB. So this is CH3 plus H forming CH4 star, stabilized to form CH4. And we showed that we finish up with this expression down here, with a high pressure limit and a low pressure limit. Now, this treatment is only approximate. It's called the Lindemann-Hinshelwood model. And it's only approximate because this reaction here, K minus A, is treated as a constant. That rate constant is treated as a constant, but it's going to depend upon the amount of energy that's there in the excited CH4 that's been formed by association. The more energy that CH4 has, the more rapidly it will dissociate. And so that's one limitation. The other limitation is that it assumes that deactivation takes place in one simple step. CH4 star collides with a third body and is immediately deactivated all the way down. But that doesn't happen. It happens in steps. And we'll talk about this much more extensively tomorrow. Both of these effects have broadened the fall-off curve. So the fall-off, what I mean by the fall-off curve is those rate constants that we showed, rate constant versus pressure. The experimental data looks something like that, but eventually if you went to higher pressures, it would tail off and look like that. But what happens is this curve gets broadened and looks more like that. So it approaches the high pressure limit and the low pressure limit more slowly than was previously the case. And this has been analyzed by a man called Jürgen Tröhr, and his technique is widely used in this fitting process. And again, I'll say a little bit more about that. Well, let's say something about it now. What he does is he takes the Lindemann-Hinshelwood expression and adds a broadening term here, this broadening term f. And log f is defined in terms of these things over here, which depends upon a quantity called f cent. And so there are now three lots of variables. We've got k naught, k infinity, and we fit those to a modified Arrhenius expression, a naught t n naught e to the minus e naught over kt. And this quantity f cent is fitted to some other complex expression here. And there's a more recent formulation of this broadening term, which was published in 2014. Okay, so that's one way of analyzing these pressure-dependent reactions. Okay, any questions, comments? Everybody's happy. Okay, I'm taking a brief rest anyway. Okay, so what we've done is we've looked at laser-induced fluorescence as a detection technique. We've looked at mass spectrometry, especially using the advanced light source and tunable radiation as a detection technique. In that case, a universal and very powerful technique. We've talked about absorption spectroscopy, and we've talked a little bit about resonance fluorescence, which is a sort of variant of laser-induced fluorescence but doesn't use a laser. Another method is what's called cavity ring-down spectroscopy, which is really rather clever. So what we've got here is radiation from a laser. So we have a pulse laser here coming in, and it goes into a cavity with two mirrors. The radiation goes into this cavity, and the light bounces backwards and forwards, and every time it hits this mirror here, some of it leaks out. And so what's going to happen is the intensity of the radiation coming out of this cavity is going to decay. And it's going to decay depending upon the reflectivity of those mirrors. The higher the reflectivity, the more slowly it will decay. Now supposing what we do is we put something inside the cell that absorbs the radiation. What will happen now is that this light pulse will decay more rapidly because every time it goes through the cell, some of it will be absorbed. And the amount that's absorbed will depend on the concentration of the species we're looking at in the cell and also the absorption cross-section, as we had before. The great thing about this technique is that the light is going back many, many times, so the effective path length is very long. And so this is a very sensitive technique for looking at radicals. And this behavior here is called the ring down time. What you do is you measure the ring down time with the laser. By laser off here, what we mean is the laser that's producing the species that's in the cell. So we've got another laser, a pulsed photolysis laser, that's going to produce material in the cell. And that will become more obvious in this diagram here. So what we've got is we've got a tunable laser here, which is used as this ring down to generate this ring down signal, which goes to this photon detector. And then we also have a photolysis laser, which in this case is a dye laser, which is used, crosses the cell and generates the reactive species within the cell. And in this case, it's been used to look at HCO. And there's the absorption spectrum of HCO. It absorbs in the 600 nanometer region, and you just pick one of these wavelengths for this tunable pulse laser here. And so this is a very sensitive technique using what's called cavity ring down. And later on, we'll have a look at an alternative way of doing this using what's called cavity enhanced absorption. One of the key things also is to determine the yields of the products. What we've been talking about is looking at the decay of the reactants, but we also need to measure the formation of the products. And so here is singlet methylene reacting with hydrogen, forming CH3 plus H. And there's the singlet methylene decaying away. It's been monitored by laser-induced fluorescence. And here's the hydrogen atom, also monitored by laser-induced fluorescence, increasing as the reaction takes place. And what you've got to be able to do, and I won't go into how it was done in this case, is you've got to be able to calibrate these signals relative to one another. But that's feasible. But it's interesting that I talked about them being a singlet methylene and a triplet methylene, the triplet being lower in energy. Triplet reacts very slowly with hydrogen. But what hydrogen can do to the singlet is it can deactivate it to the triplet. And so we not only get this reaction here, but we also get singlet plus H2 going to triplet plus H2. And by monitoring the amount of H that you get, you can determine the yield of this reaction channel here. These are experiments done at Sandia, looking at the reaction between C2H5 and O2. So here's the reaction. C2H5 plus O2 goes to C2H5 O2 star, and then that can be stabilized and form C2H5O2. In addition, this species here can dissociate and form ethylene and HO2. So HO2 can be produced in the reaction. And it's important for combustion purposes to know what that yield of HO2 is. So what they did was a very clever experiment in which they produced the ethyl radicals using chlorine atoms. So they had chlorine, they photolyzed chlorine, and it reacted chlorine to produce chlorine atoms. Chlorine reacted with C2H6 to produce C2H5 plus HCl. So that's the way they generated the C2H5. And then they looked at the amount of HO2 that was formed. It was formed very quickly at low temperatures and then decayed away. So that's its production, and that's the decay of the HO2. But what they also did was to put in methanol and generated CH2OH from the reaction between chlorine and methanol. And CH2OH plus O2 also generates HO, plus O2 also generates HO2, but it does so 100%. So every CH2OH plus O2 reaction that occurs generates HO2. So there's the HO2 produced, and provided you're generating the same amount of chlorine atoms in the two experiments, then the relative yields of these two give you the relative yield, the fractional yield of HO2 in the C2H5 reaction. Here, the yield of HO2 is 100%. Here, it's significantly less than 100%, but you can determine exactly what it is. And the HO2 yield goes up as the temperature goes up, and it also goes down as the pressure goes down. As the pressure goes down, you stabilize more and more of this C2H5O2 to generate C2H5O2 there. So this reaction gets depressed as you go down in pressure, but it gets enhanced as you go up in temperature. And this is an interesting bit of behavior here. At much higher temperatures, what's happening is some of the HO2 is produced instantaneously, as it is here, but then some of it is produced on a much longer time scale. What's happening there is, at these higher temperatures, some of the C2H5O2 that's been stabilized is now dissociating to form HO2 and C2H4. So there are two time scales coming directly from this energized C2H5O2 and also coming from stabilized C2H5O2 that's then redissociating. And this is an important observation, and we'll discuss it more tomorrow and then again on Friday. Okay, let's have a look at shock tubes. So the basic idea behind a shock tube is that you have a high pressure region here and a low pressure region here containing your reactant species. And there's a diaphragm between them. You burst the diaphragm, and a shock wave travels through this region here. Here's the shock wave traveling through, hits the wall, comes back again as a reflected shock wave. And as it moves along, it heats the stuff in this cell here basically by compression. So it's compressive heating, and it give rise to really quite high temperatures of 1, 2, 3,000 K. And these are the shock tubes, pictures of shock tubes in Professor Hansen's lab at Stanford. You can see the size of them. They're pretty big. And the key thing, well, the group is very, very careful about the way the shock tubes themselves are designed. But what they've put a lot of attention to is the way in which they detect the species that are present. So, and this is basically another dye laser system that's being used to excite fluorescence in the reaction system. But they've used many, many techniques, and we'll just mention a few of them now. So, compressive heating of the reaction mixture, and the radicals are generally formed by thermal dissociation of a precursor. So, the heating occurs, and the radicals you're interested in are formed by dissociation of a precursor, thermal dissociation now. It's a single-shot experiment. In those pulse photolysis experiments, you repeat the experiment many, many times. And that allows you to get greater sensitivity because of that repetition. In this case, it's single shot, and so you've got to have a technique which is highly sensitive for detecting the species you're looking at. So single shot, so no signal averaging, but impressive optimization of the signal. And we'll see some examples of that. You generally need to assess secondary reactions. What I said was secondary reactions occur if the radical concentrations are too high, and it's quite difficult to get those radical concentrations down sufficiently low that there are no secondary reactions at all. What you try to do is to minimize them. But you also recognize them, and what you often need to do is to use numerical chemical model and sensitivity analysis to show the viability of the measurements. And here's an example from this paper here from CH3 plus OH. And this shows the sensitivity of the OH to various reactions. So there's the reaction you're looking at, which is CH3 plus OH, high negative sensitivity, because that reaction is removing OH. Here's this reaction here is quite relatively sensitive in a positive sense, and that's because it's CH3 plus CH3 reacting together to form C2H6. So this reaction is removing CH3 from the system and so slowing down the decay of OH. And so it has a positive sensitivity for the concentration of OH. And so this allows you to understand which reactions you have to take account of in the model that you're constructing. So this is OH plus formaldehyde. And this was carried out, this is a temperature of 670 K, 1.6 atmospheres, and taking place behind reflected shock waves. So the shock wave has gone through, come back again, and so the temperature has been increased in the initial wave, but then it's increased again when the second wave comes through, the reflected wave comes through. So you get a higher temperature with this in these reflected shock tube experiments. And OH concentration time histories were determined by laser absorption using this particular line in the OH band. And so this enables them to determine the absolute concentration because they're doing an absorption experiment. It's not a laser-induced fluorescence experiment, it's a laser absorption experiment. Other reactions contribute to the OH time profile, especially CH3 plus OH. The OH is produced from tertiary butyl hydroperoxide, and there is some CH3 formed from that reaction. And then the rate coefficient is determined by fitting to a detailed model. They use what's called GRI-MEC, which we'll talk about later in the week, with the addition of some acetone chemistry deriving from the dissociation of the OH precursor. So this also not only produces methyl, but it also produces acetone, which can also react with the OH. And they do a detailed uncertainty analysis. The care that they take in the analysis of the data is really incredibly impressive. So here's a decay of OH. And here are the sensitivities. So that's the sensitivity with respect to OH plus formaldehyde. And here's the sensitivity with respect to OH plus CH3. And these are the origins of the uncertainties in the rate constant. So the time zero, they need to define the time zero because that's how they're going to determine the starting point for all the various radical processes that are occurring. The fitting uncertainty, the uncertainty in fitting the model to this decay, uncertainty in the absorption coefficient. They need to know exactly how much OH is there because that's going to determine the concentrations of the secondary species. The wave meter reading, the setting of the absorption laser, the uncertainty in making up the mixture, the uncertainty in the temperature, and then the uncertainty in that secondary reaction, OH plus CH3. And that's the major contributor to the overall uncertainty. But you can see there's the best fit, and here's the effect of halving the rate constant, and there's the effect of doubling the rate constant. So you can see that rate constant is really very, very well defined. And here's the data that they determined for OH plus formaldehyde, and the best fit modified Arrhenius plot through their curves, going from temperatures of about 1600 K down to 900 K. And this is a whole set of experimental data, their own data up here, and then lower temperature data down here from a whole host of different sources. And again, it shows rather similar behavior to that we found for OH plus acetone early on, increasing with temperature at high temperatures and then increasing with decreasing temperature at low temperatures. And there's the expression for the rate constant they obtain. OH plus aldehydes, they've done a lot of work on measuring OH plus aldehydes, use the same absorption technique over this temperature range, and there is some dissociation of the aldehyde at higher temperatures, which can again complicate the kinetics, and so they monitor the amount of that by looking at CO. So there's the decay of OH, and here's the absorption by CO, which is they use to determine the amount of the aldehyde that's dissociated. And once again, there's the decay and the best fits going through it, and then the effect of changing the rate constant there. So they're changing the rate constant by plus or minus 30%. And again, an analysis of the uncertainties, mixture composition, fitting uncertainty, OH absorption coefficient times 0, uncertainties in pressure and temperature, and then that CH3 plus OH reaction, which isn't making such a big, having such a big effect here. And they've done this for a whole range of aldehydes there. This is the technique that I was mentioning earlier on. So this is what's called cavity-enhanced absorption spectroscopy. And so you have a laser coming in here, and they're looking at CH3, and that laser bounces backwards and forwards before it goes to a detector. You're not measuring the ring down time now, you're just measuring the amount of light that's absorbed. But because it bounces backwards and forwards many, many times, the path length is very long. This R equals 0.98 refers to the reflectivity of these mirrors. So the reflectivities are very high, so you're going to get the light going backwards and forwards many, many times, and a long effective path length. And the laser is very narrow, and this is the absorption at high temperatures by the methyl radical. It's very broad, but they look very close to this peak in the absorption at that point there. And then these are two decays of CH3 using this technique. And here's the detectivity of the order of 0.1 parts per million at the lower temperatures, rising slightly as you go up in temperature. And remember what I said, that the more sensitive you make your technique, then the less important will be the secondary reactions. And so that was the impetus behind developing this technique. And you can see how much more sensitive it is than methods that have been used previously. A factor of 10,000 more sensitive than these methods that were used up here. And this is a reference to some measurements made on CH3 plus H by shock tube reactions that I mentioned, the CH3 plus H that was done by Mark Brouard at lower temperatures. These are higher temperature measurements, and I'll refer to these later on tomorrow when I talk about theory. But that's just a reference to the way in which the measurements were made. Okay, just let's look quickly through use of flow tubes. So this is, again, a difficult experiment to do because it involves a reaction between an atom and a radical. So two radical species, an atom and this radical here. And what it uses is a technique that's been widely used in what is called a technique of discharge flow. So you pass the gases, in this case nitrogen, diluted in argon, through a microwave discharge. And this microwave discharge generates nitrogen atoms. So it's at relatively low pressures, and you pass the material through the discharge, generates nitrogen atoms, and you add NO, and the NO reacts with the nitrogen and generates O plus N2. So that's the way in which they generate the oxygen atoms. Then what they also do is add some water. And then they inject some chlorine gas into that mixture down here. And they don't use a laser, they use the flash lamp. So this is a pulse of light that dissociates the chlorine molecules. And so what happens is that chlorine is dissociated to form two chlorine atoms, and then chlorine reacts with water to produce OH plus HCl. So that's the way in which they generate their OH. By photolysis. And so they're in this region here, what they've got is oxygen atoms coming down here, and then they generate OH because they put chlorine in and they've photolyzed it. And they can determine the amount of oxygen they've got in from the amount of NO that they've added here. It's called a titration method. And they monitor the amount of OH using resonance fluorescence. Again, this is rather like, as I said before, rather like the laser-induced fluorescence technique. So basically, this is a lamp that excites the OH fluoresces, and you measure it as a function of time. And you do it in the presence of a large concentration of oxygen atoms. Okay, I'll show you the results from this experiment later on today. And then this is a different sort of flow experiment. This is looking at the pyrolysis of butanol. This is done in China at NSRL. And what they've got is a heated vessel here. And this is the temperature as you go along this cell here. 1000 K, heat it more, 1200 K, 1400 K. So the temperature isn't constant throughout the cell, but it's well defined and it's measured as you go along this cell here. And so the butanol comes through here, dissociates, and then you have a pinhole and a skimmer, and then you use vacuum ultraviolet light from the synchrotron and the time of flight mass spectrometer. And you can detect many, many species using this synchrotron radiation. So this shows, as a function of different pressures, the amount of butanol that's present, decaying away slowly at low pressures and more rapidly at high pressures. And this is butene and CH3 and C6H6, all measured using this mass spectrometry technique. So this is again a flow method, but looking at an overall dissociation process. And these are the sensitivities of the various reactions with respect to the amount of butene that's formed. And so the amount of butene that's formed depends upon many reactions, but some of them are much more sensitive than others. And so by fitting these rate constants, so here's the butanol coming down here, here's the butene formed here at different pressures, and these are the fits using different models. So this is a technique that enables you to determine a wide range of rate constants, but it's dependent upon having a good model and worrying very much about the sensitivities. And this is using, as before, that photon energy method, looking at the onset of the ionization. And so this is an experiment looking at the oxidation of cyclopentene in a flow tube again, as we had previously, and looking at different products cyclopentene 1-ol, cyclopentanone, cyclopentene 2-ol, pentene 4, pent-4-enal. And so these are 3 different products here, these 3 here, and they didn't detect this pent-4-enal there. So again, a lot of information coming from the use of synchrotron radiation, this time in conjunction with this flow tube. Final point before we break. So these are those old experiments that I was telling you about. So they come from the 1970s, and these experiments were widely used to develop our initial understanding of autoignition chemistry. And this group really laid many of the foundations for our understanding of autoignition. And so one of the things they did was to take a mixture of hydrogen and oxygen, which was reacting slowly, and then add an alkane to it and look at the products. And so this mixture of hydrogen and oxygen gave them OH, H, HO2, and allowed them to look at the reactions of those species with these alkanes RH in a very, very well-controlled environment. They looked at the oxidation of aldehydes as a source of alkyl radicals and looked at the oxidation of them in the presence of O2, looking at the products. So this is all using gas chromatography to determine the products. And then finally, they used tetramethyl butane in the presence of O2, which acts as a source of HO2. So they looked at HO2 chemistry using this. Okay, what we will do after the break is we'll look at the use of some of these techniques to study various aspects of the hydrogen-oxygen reaction. But at this stage, are there any questions? Does anybody have any burning issues that they want to raise? You're not very good at raising burning issues, are you? It's been a long day. Okay, so we come back at 4:30, and then we only have 1 hour to go.